Particle image velocimetry, or PIV, is an optical method of measuring velocity fields. In this video, we'll take a look at the hardware and measurement technique in general, and we'll also look at the specific system called EDU PIV. First, we'll look at the hardware requirements for general PIV, or particle image velocimetry. Here we're shown that PIV usually is a 2D image. Sometimes it may be 3D, but in this case we'll look at a 2D system, meaning that it calculates velocity components in the x and y directions. This is a diagram of what a PIV setup might look like. In the center we have the black dots, which represent the particles or seeding in the flow. The green represents a laser or a light source. On the right is the laser itself in the mirror or optic setup to create the light sheet. And then at the left is the camera or a PIV detector. Now we'll look at an experimental setup for PIV using the EDU PIV system. In the diagram we see similar to the previous image, but now we've added the pump and the nozzle, which create the flow that we will be imaging. The nozzle is 3D printed and attached to the pump, and on the other side of the pump is a cord that leads to the flow controller, where the user can control the waveform, either sine, square wave, or constant flow, as well as the speed of the flow. And on the right are the other elements, the camera, the LED illumination, and the pump. For this system, it uses an LED light source instead of laser, because a laser is more dangerous to the human eye. So in this case, when it's used in university settings, it's safer to use LED light source instead of laser. This video will show what a measurement volume looks like. Imagine that the large blue cube is the full flow field, where water or another fluid is flowing. The camera images only a 2D plane within this 3D volume. And when we rotate, we'll see the white portion, which is representative of the laser or LED light sheet, illuminating a 2D plane within the volume. This slide shows the seeding particles and some specifications about them. They're very small, ranging from 1 to 70 micrometers, and they're neutrally buoyant, which means they go along with the streamlines of the flow field. That means they don't alter the movement of the water or other fluid itself. This is a listing of the hardware used in the EDU PIV setup. We talked about the LED light sheet, the seeding particles, and the camera. This video will show an example of some PIV data that might be acquired. The small white dots are the seeding particles, and then we notice two vortices, one at the top and one at the bottom, but we can't tell much more detail about that. To do so, we need a quantitative way of analyzing the flow, which is where PIV comes in. This grid represents the different areas where vectors will be calculated. For each grid section, one vector will be calculated, and we'll see that in the upcoming image. Here we see one arrow within each square, or interrogation area. Some cameras have a special mode called double frame mode, where they take two images within a very small amount of time. Most other cameras, as with the EDU PIV system, will just have a single frame mode, where they take images closely in time at a constant rate. These two images, the one labeled T and the one labeled T plus dt, show two instants in time very close together. The one with dt added is the next time step, and the one with just t is the previous time step. The particles will move a certain distance between t and the next time step t plus dt. And the distance these particles move, combined with the known time step, allows us to calculate velocity. This video will show a demonstration or a visual representation of the algorithm used to calculate vectors within each interrogation area. As we said before, the one labeled t represents the previous time step. The one labeled t plus dt is the next time step. The little white particles, or the empty areas on the gray square, represent particles within each time. The computer compares the two to try and find the match, or the best match possible, between the two time steps. Once it finds this, it can calculate how far the particles moved in the x and y direction. Then it calculates a final vector. Another element we need is a scale factor to be able to compare the pixel size versus the real world size. In this case, we have a ruler serving as our scale reference, so we know how big a pixel represents in the real world. And the final result is, again, as we said, one arrow within each interrogation area. Now we'll look at example data obtained with the EDU PIV system. Again, we have the original images obtained by the camera with the particles moving in the flow created by the pump and nozzle. We'll add the grid in so that we can see where vectors will show up in each interrogation area. And then through the post-processing algorithm, also known as cross-correlation, we calculate what the arrow should look like within each interrogation area. One additional factor is a question of, can we increase the spatial resolution, or can we get more detail about the arrows within these areas? If we were to try that, we may encounter an issue where we get erroneous arrows or incorrectly calculated velocities. The reason for this is because sometimes if you have too small of an area, as is the case with the 32 by 32 pixel interrogation area, the particles may move outside of the area before the velocity can be calculated. So in this case, the 64 by 64 pixel interrogation area is the best choice.